This video is about the algebraic manipulation method called completing the square. We'll talk about why we need this new method, how it works, and whether there's any flexibility in that process. So the goal of completing the square is to rewrite a standard form quadratic in graphing form. So standard form is y equals a times x squared plus b times x plus c, where a, b, and c can be anything, although a cannot be equal to 0, or else we would lose our x squared term and it wouldn't be a quadratic anymore. Graphing form is y equals a times x minus h squared plus k. And remember that the a, h, and k are all representative of certain transformations that have happened. So if you don't remember how graphing form works or what it means, check out that other video. So the reason we need to use this method is that we're going to want to find the vertex of a function, and we're not always going to be able to use our old methods. So what we know how to do right now is to find the vertex by relying on the fact that parabolas are symmetrical, and the vertex lies on the line of symmetry, and that line of symmetry is exactly halfway between the two x-intercepts. So what we usually do is try to find those x-intercepts and then average them to get the x value of the vertex. So this would be the average of the x-intercepts. And then plug that x value back into the function to get the y value of the vertex. So let's try that here. If I want to find the x-intercepts, I know that's when y equals 0. So I'm going to plug in 0 for y and solve for x. Now I've got a quadratic expression set equal to 0, so I have a couple options. What we're usually used to doing is trying to factor the quadratic expression and use the zero product property. So I'm going to try that. I'm going to go through this process quickly, but remember that there is a separate video about factoring quadratic expressions if you want to review. So this one we want to add to 2x and multiply to 4x squared. The terms that multiply to 4 are 1 times 4, 2 times 2, negative 1 times negative 4, negative 2 times negative 2. But I see that when I try to add up any of those pairs, none of them add to positive 2. So we're in this place where the quadratic expression is not factorable, which means we can't use the zero product property to solve. We have one other method. Well, we actually have two other methods. We could use the quadratic formula, but I'm first going to check Desmos. So when I plug in y equals x squared plus 2x plus 4 to Desmos, I actually see that there are no x-intercepts here. So my whole method was based on the idea that I could average the x-intercepts to find the x value of the vertex. And because there are no x-intercepts, I can't do that. So we need to come up with a new method, and that method is called completing the square. So remember that graphing form of a quadratic is y equals a times x minus h squared plus k. And when I look at this, I see that the only x in that whole equation is inside of that x minus h squared. So if I just look at that for a minute, I could write that as x minus h times x minus h, and I could represent that in an area model if I wanted to. So the really important piece, or the really important component of this, is that the area model is a perfect square because the length of the base and the length of the height are the same length, they're the same value. So what I need to do is try to get all of the x squared and x terms in my equation into a perfect square so that I can write it in graphing form. So what I'm going to do is I'm going to start to think about this with algebra tiles, and then we're going to also show how it works in an area model, because ultimately we don't want to have to rely on the physical algebra tiles. So I'm going to start by getting out an x squared, 8 x tiles, and 3 units. And I want this to be equal to y. So I'm going to put this double yellow line down the middle, and that's my equal sign. So now I'm physically representing the equation y equals x squared plus 8x plus 3. And what I'm going to do now is try to arrange the tiles in such a way that all of the x squared and x tiles are creating a perfect square where the length of the base is the same as the length of the height. So if I put the same number of x tiles above and to the right of my x squared tile, then what I'm doing is I'm building a square that has that property, that has the same base length and height length. And what I'm realizing as I do this is that all this means is that I'm splitting up the x tiles so that half of them are above the x squared and half of them are to the right of the x squared. Okay, and then 3 of my unit tiles will fit in here, but I'm going to see that there's some empty space that I'll need to fill. Okay, so if I were drawing this with an area model, I would see that half of my 8 x tiles, 4x goes in each of these spots. And so I'm working towards a square that has a base length of x plus 4 and a height of x plus 4. Now what I would need to complete this square are 16 units, but I only have 3 units. And so what I'm going to do is I'm going to add 13 more units to each side. So I'm just going to draw this in here. Okay, and so I added my 13 unit tiles in my square to complete it, and I added my 13 unit tiles to the left side of the equation, which now says y plus 13. So I've got y plus 13 equals x squared plus 8x plus 16, which is exactly the same as what's in my area model. So I can rewrite that area as x plus 4 times x plus 4, or x plus 4 squared. Okay, and now I'm one step away from having it in graphing form. I just need to subtract 13 from both sides now. So I get y equals x plus 4 squared minus 13. And now I can see that the vertex is at -4, -13. And I'll definitely want to check that by graphing the original function in Desmos. And when I do that, I see y equals x squared plus 8x plus 3 does have a vertex at -4, -13. So this is the process that we're going to follow, but we're going to look at a bunch of examples that get progressively more complicated for various reasons. And so if you don't need practice with these early equations, you can skip ahead and try some harder ones. So here I've got y equals x squared minus 6x minus 2, and I want to determine where the vertex is, and I'm going to do that by using the method completing the square. So here I've got negative x tiles, and so it no longer makes sense for us to use the physical algebra tiles. So what I'm going to do is I'm going to draw my perfect complete square and fill in as much of that as I can. I've got an x squared. I know that I've got 6 negative x tiles, and so I want to put half of them above and half of them to the right of the x squared, so that the base length is x minus 3 and the height length is x minus 3. So what this shows me is that I need 9 unit tiles to complete my square, but I only have -2. So I'm going to add 11 units to both sides of my equation to keep it balanced. And I'll get y plus 11 equals x squared minus 6x plus 9. So that's the same as the area of my complete square, my area model. And so I can rewrite that area as x minus 3 squared. But of course I still have this plus 11 units with the y, so I need to subtract 11 from both sides. Y equals x minus 3 squared minus 11 is my final equation, and so I know that the vertex is at positive 3, negative 11. The next example is y equals x squared plus 5x plus 1. And the dilemma here is that when I start to build my perfect square, I need to figure out how to split up 5 x's into 2 equal sizes. So this is totally fine. 5 divided by 2 is 2.5. So I'm just going to put 2.5x in both of those spaces. This is where using the physical algebra tiles would break down because we can't snap those in half. So that's one of the reasons why it's important to switch into a two-dimensional representation of the three-dimensional algebra tiles. So the dimensions of my square are x plus 2.5 times x plus 2.5. We're checking that the base and the height have the same length, and they do. And then 2.5 times 2.5 is 6.25. So I need that many unit tiles along with the x squared and the 5x on the right side of my equation. So I need to add 5.25 more unit tiles to get that perfect square. And so I'm going to do that. Oops. Y plus 5.25 equals x squared plus 5x plus 6.25, which is the same as the area of my perfect square. So I get y plus 5.25 equals x plus 2.5 squared, and then I just need to subtract the units out to get y equals. So the vertex here is at negative 2.5, negative 5.25. And when you're doing these, you should plug your function back into Desmos to check that you got the correct vertex, or else you know to go back and double check the algebraic manipulation that you did. Okay, so here's the next level of complicated. We've got 2x squared tiles now. So if I were trying to do this with the physical tiles, I would have my 2x squared tiles, and I could either place them next to each other like this, or on top of each other like this. But either way, I'm seeing that the length of the base and the length of the height are not the same. So here the length is 2x, but the base is only x. And if I turned it sideways, it would just be the reverse. So we need to figure out how to get rid of one of those x squared tiles without moving x tiles to the left side of the equal sign. So what I'm going to do here is divide the entire equation by 2. So I'll have y divided by 2 equals 1x squared, and that's what we wanted, plus 4x minus 5. And then I'm just using my regular process of completing the square. So I'm going to draw my perfect square so I know how many units I need. Half of 4x is 2x. And so my base length is x plus 2, my height is x plus 2, and I need 4 unit tiles because 2 times 2 is 4. So I have negative 5 unit tiles, which means I need to add 9 to both sides of my equal sign. Half of y plus 9 is equal to x squared plus 4x plus 4, and that's my perfect square. So now I can write half of y plus 9 equals x plus 2 squared. And now it's just a matter of solving for y. So I'm going to make a little bit of space here. And first I'm going to subtract 9, so half of y equals x plus 2 squared minus 9, and then I'm going to multiply by 2. So y equals 2 groups of my perfect square and 2 groups of negative 9, which is negative 18. So my vertex here is at negative 2, negative 18. and I can see that I've got a vertical stretch of 2, which means that the parabola here is skinnier than the parent function, y equals x squared. So I just have one last example, and I want to use it to think about whether we can do this process in a different order. So y equals 3x squared minus 12x plus 5. And if I started here by drawing my perfect square, I would quickly realize that I had 3x squareds, and that was a problem. So just a little reminder that in graphing form, there is no coefficient on the x term inside of the parentheses. So even if I had something like 4x squared, which I could use to create a perfect square, I still need to divide out that coefficient because the goal is to put it into graphing form. So I'm going to start by dividing the whole thing by 3, and I've got y equals x squared minus 4x plus 5/3. Oops, and that's y divided by 3 on the left side. So I'm seeing this 5/3 on the right side of my equation, and I'm fine with fractions. I can work with fractions, but it seems like there might be a more efficient way to do this. So I'm just going to go back to looking at my original equation here, and oops, let me rewrite that. Y equals 3x squared minus 12x plus 5. So what I'm going to do is first just move over my units, because they're the piece that when I divided by 3, I didn't get an integer. So y minus 5 equals 3x squared minus 12x. And now I can take that step of dividing everything by 3. So 5 less than y divided by 3 is equal to x squared minus 4x. And now I'm in a space where I can make my perfect square. And I see that the dimensions are x minus 2 times x minus 2, which gives me a units term of 4. So I could then add 4 to both sides and get 5 less than y divided by 3 plus 4 equals the square x minus 2 squared. And then I can go about that process of putting everything back when I solve for y. So 5 less than y divided by 3 equals x minus 2 squared minus 4. And then I'm going to multiply everything by 3, remembering that I'm multiplying my perfect square and the units term by 3. And then I'm going to put those units back. So 3 times x minus 2 squared. And then I had minus 12. I'm adding 5 more, so that's going to be minus 7. And my vertex is at 2, negative 7. Okay, so we can do the process by dividing out the a value first. We can move the units first. And there are even a couple other ways. So if you understand that you're trying to make a perfect square, then you can use a little bit of flexibility in your process, and that's totally fine as long as it makes sense to you. So make sure that you try some more examples if you still think you need practice, and email me if you have any questions.